Some planets never see a sunrise. No morning, no sunset, no seasons, just darkness. Somewhere between the stars, far from any solar system, there may be worlds drifting completely alone. No parent star, no warm light, no familiar orbit. These are rogue planets. At first, they sound impossible to survive on. A planet without a sun should be frozen, lifeless, and dead. But some rogue planets may still hold heat deep inside. Some may hide oceans beneath thick ice. Some may have atmospheres strong enough to trap warmth for billions of years. So tonight, we ask a strange and haunting question. Could humans survive on a rogue planet? Before we go deeper, if you enjoy calm, cinematic space documentaries made for sleep, mystery, and deep cosmic questions, make sure to subscribe to Theories Before Sleep. Because tonight, we are leaving behind every world we understand and traveling into the darkness between the stars. A place with no sunrise, no daylight, no warmth from a sun, only frozen silence, distant stars, and the possibility that even there, humanity might one day build a home. A rogue planet is one of the loneliest things the universe can create. Not because it is small, not because it is broken, but because it has no star, no sunrise waits beyond its horizon, no daylight sweeps across its surface, no familiar warmth arrives from the sky. It simply drifts, alone, through the dark spaces between stars. A rogue planet, also called a free-floating planet, is a planet that is not gravitationally bound to any star. It does not orbit a sun the way Earth orbits ours. It moves through interstellar space, untethered, carried by its own momentum through the galaxy. NASA describes rogue planets as free-floating exoplanets that are not attached to any star in course. At first, that idea feels almost impossible, because when we think of planets, we imagine systems. A star in the center, planets circling around it, moons circling planets, light, heat, order. But rogue planets are different. They are worlds without a home system, worlds without a sky, ruled by a nearby sun, worlds that have either been violently thrown out of their original solar systems or perhaps formed alone, directly from collapsing clouds of gas and dust, more like tiny failed stars than ordinary planets. And that is what makes them so strange. They challenge the very meaning of the word planet, because a planet, in our imagination, belongs somewhere. A rogue planet belongs nowhere. For a long time, scientists suspected these worlds existed. Planetary systems are chaotic when they are young. Giant planets migrate. Smaller planets are pushed and pulled. Close encounters can fling worlds outward at incredible speeds. In a young solar system, gravity can act like a slingshot. One planet passes too close to another. Its orbit becomes unstable. It is kicked outward, farther, faster, until eventually it escapes its star completely. And after that moment, there is no return. The planet becomes a wanderer, a dark world crossing the galaxy alone. But finding rogue planets is extremely difficult. A normal planet can be discovered because it orbits a star. It may block a little starlight when it passes in front of its star, or it may tug on the star with gravity, or it may reflect light. A rogue planet gives us almost nothing. No star to dim, no bright light to reflect, no easy orbit to follow. Most of them are incredibly dark and cold. They are hidden in the blackness between stars, where even powerful telescopes struggle to see them. So scientists often detect them indirectly. One of the most important methods is gravitational microlensing. This happens when a rogue planet passes in front of a distant background star from our point of view. The planet's gravity bends and magnifies the star's light. For a short time, the rogue planet may be invisible, but its gravity leaves a temporary fingerprint, a brief brightening, a tiny distortion, a signal that something dark passed between us and a distant star. That is how we know some of these worlds are out there, not because they shine, but because they bend light. And as astronomers improved their surveys, the numbers became shocking. Some studies suggest that rogue planets may be incredibly common. NASA reported an estimate that the Milky Way could contain about 20 times more rogue planets than stars, possibly trillions of wandering worlds. In COS, think about that. The Milky Way contains hundreds of billions of stars, and there may be even more planets drifting between them, not orbiting, not shining, just moving silently through the galaxy. If that estimate is even close to correct, then the galaxy is not only filled with stars, it is filled with invisible worlds, worlds we almost never see, worlds that may outnumber the lights themselves. This changes the way we imagine space, because the darkness between stars may not be empty. It may be crowded with planets, frozen Earth-sized worlds, dead rocky worlds, gas giants without suns, icy planets wrapped in thick atmospheres, massive wanderers still glowing faintly from the heat of their formation. Rogue planets are not all the same. Some may be rocky and small, similar in size to Earth or Mars. Some may be icy, with thick frozen crusts covering hidden interiors. Some may be gas giants like Jupiter or Saturn, thrown out of their systems before they could settle into stable orbits. Some may be young and warm enough to glow faintly in infrared light. Others may be ancient, dark, and nearly impossible to detect. A young rogue gas giant might still radiate heat left over from its birth. It might glow weakly in infrared, like an ember cooling in space. But an old rocky rogue planet would be much harder to find. It would reflect almost no light. It would emit almost no heat. It would be a planet hidden in darkness, a world that could pass through interstellar space for billions of years without ever being seen. And yet, it could still exist. That is the haunting part. There may be Earth-sized rogue planets wandering the Milky Way right now, completely invisible to us. Some may have once had skies, oceans, moons, maybe even warmth. Then, something happened. A gravitational encounter, a violent instability, a close pass with a giant planet, and they were thrown away. Imagine a young planet forming around a star. For millions of years, It circles in a system filled with dust, gas, and other worlds. Then, one day, its orbit changes. Slowly at first, then suddenly, it is pulled into a dangerous path. Another planet passes close. Gravity grabs it, twists it, accelerates it, and the world is launched outward, past the outer planets, past the weak edge of its star's influence, until the star that once warmed it becomes just another point of light. Then even that point fades into the galaxy. The planet becomes rogue, a world without sunrise, a world without seasons, a world without a parent star. And from that moment onward, its surface enters a different kind of existence. If it had oceans, they would freeze. If it had an atmosphere, parts of it might collapse onto the ground as frost, unless the atmosphere was thick enough to trap heat. If it had life, that life would face a terrible transformation. The surface would become dark. The sky would become star-filled. The planet would no longer measure time by days and years in the familiar way. There would be no sunlight crossing the horizon, only darkness. And yet, even in that darkness, not every rogue planet must be completely dead. Some may retain internal heat. Large, rocky planets can produce heat from radioactive decay inside their interiors. Gas giants can hold heat from their formation for billions of years. Some worlds may have thick hydrogen atmospheres that trap warmth like a blanket, and beneath frozen crusts there may be oceans, hidden oceans protected from space by ice, heated from below by internal energy. A rogue planet could be frozen on the outside, but still active deep within. This is where the question becomes unsettling, because if a rogue planet can keep heat, if it can preserve liquid water beneath ice, if it can hold an atmosphere, then maybe survival is not completely impossible. Not on the surface, not naturally, but perhaps underground, perhaps inside habitats, perhaps near geothermal vents, perhaps using nuclear power, deep drilling, and closed life support systems. But before we ask whether humans could survive there, we must first understand what these worlds truly are. They are not rare mistakes. They may be a major population of planets in the galaxy. They may form through violence or through isolation. They may be small and rocky, or massive and gaseous. They may be frozen completely, or hiding heat beneath their surfaces. They may be ancient, older than Earth, older than our solar system, wandering through the Milky Way since before our sun was born. And because they are so difficult to detect, scientists are only beginning to understand them. Future telescopes may reveal many more. NASA's Nancy Grace Roman Space Telescope is expected to help discover hundreds of Earth-mass rogue planets and improve estimates of how common these worlds really are. Cooker. That means our picture of the galaxy may soon change. We may discover that stars are only the visible part of the story. Between them, hidden in darkness, are planets, worlds without light, worlds moving through space like silent ghosts. And there is something poetic about that. A planet with no sun is almost difficult to imagine emotionally, because every world we know is defined by light. Earth has the sun, Mars has the sun, Jupiter Saturn, Uranus, Neptune, even far away, they still belong to our star. But a rogue planet does not. It has no dawn, no golden hour, no warm side facing the light, no star rising over mountains, no sunsets turning clouds red. Only night. A night that may last billions of years. If you stood on its surface, protected inside a suit, your sky would be unlike anything humans have ever seen. There would be no bright sun, no blue, no familiar moonlight, just stars, millions of them, brighter than we see from Earth, because there is no daylight, no city lights, no atmosphere perhaps, no nearby star to wash them away. The galaxy itself might stretch overhead like a glowing river, beautiful, but cold, and beneath your feet would be a world that does not belong to any solar system, a planet moving alone between stars. That loneliness is what makes rogue planets so haunting. They are not destroyed. They are not gone. They continue. They orbit the galaxy itself, silent passengers in the Milky Way. And somewhere out there, one of them may be rocky. One may have ice. One may have heat. One may have an ocean. One may even have chemistry happening in darkness, far from any sun. So, the question that drives this story is not simple. It is not just whether a rogue planet exists. It is whether a world without a star could ever become a place where humans survive. Could we land there? Could we build there? Could we find energy? Could we melt ice into water? Could we grow food under artificial light? Could we live without sunrise? Could the human mind endure a planet where every day is night? That is the mystery of rogue planets. They are not only scientific objects, they are tests of imagination. They force us to ask what a planet really needs. Does it need a star to matter? Does it need light to be alive? Does it need a sunrise to become a world? Or can a planet drift through the dark for billions of years, silent, forgotten, and still hold secrets beneath its frozen skin? That is why rogue planets matter, because they remind us that the universe is not only made of what shines. Some of its most mysterious worlds may be hidden in the spaces between the lights. And if humans ever tried to survive on one, we would not just be leaving Earth, we would be leaving the idea of daylight itself. A rogue planet does not begin as a lonely world. At least, not always. Most of them may begin inside ordinary young solar systems, surrounded by dust, gas, newborn planets, and a young star still burning through its earliest life. At first, everything seems to belong somewhere. The star sits at the center. The planets form around it. The disk slowly clears. Orbits begin to settle. But early planetary systems are not peaceful. They are chaotic, crowded, unstable. Young planets do not form in perfect order. They pull on one another. They migrate. They change position. They disturb smaller worlds. And when several large planets form in the same system, gravity becomes dangerous. This is the first major way rogue planets are born. Ejection. A planet forms around a star, and then another planet throws it away. This happens through close gravitational encounters. One planet passes too close to another. Their gravity interacts. energy is exchanged. One world may move inward, another may be pushed outward, and if that outward push is strong enough, the planet can reach escape velocity. It leaves the star forever. NASA describes this kind of world building as chaotic, with lighter planets sometimes being flung away from their stars by gravitational interactions. Those ejected planets then begin a solitary existence in the darkness between stars. In Span, imagine a young Earth-like planet in another solar system. For millions of years, it circles its star. Maybe it has a crust. Maybe oceans are beginning to form. Maybe its atmosphere is thickening. Then, a giant planet moves. A Jupiter-sized world migrates inward or outward through the system. Its gravity disturbs everything near it. Smaller planets are pulled into new paths. Their orbits stretch. They become elliptical, dangerous, unstable. Then comes the close encounter. Not a collision, just gravity. A massive planet passes close enough to grab the smaller world gravitationally, twist its orbit, and accelerate it outward. The smaller planet begins to fall away from the inner system. At first, the star still dominates. The planet is still bound, still returning, but another encounter happens. Or the orbit stretches too far. And finally, the star loses its grip. The planet is no longer a member of the system. It becomes rogue. This is one of the most violent things that can happen to a planet without destroying it. The world survives, but everything that made it familiar is taken away. No stable year, no sunrise, no seasons, no central star growing warm in the sky. Only motion outward into darkness. In our own solar system, Jupiter shows why giant planets matter so much. It is massive enough to shape the asteroid belt, redirect comets, disturb small bodies, and dominate the gravitational architecture around it. But we should be careful with one idea. Jupiter did not, literally, almost eject Earth. In the solar system we live in today, Earth remains stable. But Jupiter's gravity shows the kind of power that can make or break planetary systems. In other systems, especially young, unstable ones, a Jupiter-like planet can absolutely become the reason smaller worlds are thrown into interstellar space. So when we imagine a rogue Earth, we are imagining a world that lost a gravitational war, not because it was weak, but because it came too close to something bigger. There is a second way rogue planets may be born. Some may never belong to a star at all. Instead of forming inside a planetary disk around a star, they may form alone, directly from collapsing clouds of gas and dust. This would make them similar to stars in origin, but too small to become stars. A star forms when a cloud of gas collapses under gravity and becomes massive enough to ignite nuclear fusion in its core. A rogue planet-like object could form from a smaller collapse. Enough mass to become a planet-sized object. Not enough mass to become a star. Not even enough to become a proper brown dwarf. Just a lonely, planetary mass body, born in darkness, never warmed by a parent sun. These objects blur the line between planet and failed star. If something forms alone like a star, but has the mass of a planet, what should we call it? A rogue planet, a sub-brown dwarf, a free-floating planetary mass object. The language itself becomes difficult. Because the universe does not always respect our categories. Some rogue worlds may be planets that were exiled. Others may be star-like objects that never grew large enough to shine. Both drift alone. Both are dark. Both move through the galaxy without orbiting a star. But their origins may be completely different. Then there is a third way. Rogue planets can be freed, not by another planet inside their own system, but by a passing star. Stars are far apart today, but they are not fixed forever. They orbit through the galaxy. They pass near one another, and in the crowded birth clusters, where many stars form together, close stellar encounters are much more common. Imagine a young solar system with several planets forming around a star. Then another star passes nearby, not close enough to collide, but close enough for gravity to reach across the system. The passing star pulls on the outer planets. Their orbits stretch. Some are destabilized. One world is dragged outward. Another is thrown into a crossing orbit. The system is disturbed, and after the passing star moves away, one planet may never return. This is how a planet can be stripped from its system. Not because of something it did, not because of internal chaos alone, but because another star passed too close, a brief gravitational encounter, and a world loses its sun. This kind of event would be most likely in the early life of star systems, when stars are still close together inside stellar nurseries. Later, after stars spread apart through the galaxy, such encounters become rarer. But by then, the damage may already be done. Many rogue planets may have been ejected billions of years ago. Some may have been thrown out when their systems were young. Others may have been freed during the violent rearrangement of giant planets. Some may be older than Earth. Some may have wandered through the Milky Way since before our sun existed. That is what makes them so haunting. A rogue planet is not only far from light, it may have been far from light for a very long time, billions of years. Imagine the ejection event itself. At first, there is a star, a young system, dust still glowing faintly around it, planets moving through unstable orbits. Then, one world is thrown outward. From its surface, if anyone could stand there, the star would begin to shrink. At first, it would still be a sun, bright, dominant, a point of warmth in the sky. But as the planet moves farther away, the star becomes smaller, the light weakens, the sky darkens, the surface temperature drops, oceans, if they exist, begin to freeze, clouds collapse, atmospheric gases may condense, the world enters a long night. Eventually, the star becomes just one point among many. Then even that emotional connection disappears. The planet is no longer orbiting a sun. It is orbiting the galaxy, a world transformed from planet into wanderer. And once it enters interstellar space, its journey may continue almost endlessly. There is very little to stop it. Space between stars is vast. A rogue planet can drift for millions, billions, even tens of billions of years. It may pass near other stars. It may cross spiral arms. It may move through clouds of gas. It may wander through regions where new stars are forming, but most of the time, there is only darkness. No sunlight, no warm horizon, no star pulling it into a year. Just gravity from the galaxy itself. A slow, silent orbit around the Milky Way. And there may be an unbelievable number of them. NASA reported research suggesting the Milky Way may contain far more rogue planets than star-bound planets, with one estimate placing them at about 20 times more numerous than stars, possibly trillions of wandering worlds. That same work suggests NASA's Roman Space Telescope could find hundreds of Earth-mass rogue planets when it surveys the sky. In COS, that means rogue planets may not be rare accidents. They may be one of the most common kinds of world in the galaxy. The lights we see at night may only be part of the story. Between those lights, there may be countless dark planets, invisible, frozen, unmapped, moving silently through space. Some may be gas giants, still glowing faintly in infrared from heat left over from formation. Some may be icy worlds, some may be rocky, Earth-sized planets, almost impossible to see unless they pass in front of a distant star and briefly bend its light. That method is called microlensing. A rogue planet passes between us and a background star. Its gravity bends the star's light. For a short time, the star appears to brighten or distort. The planet itself may remain unseen, but its gravity reveals it. NASA explains that microlensing lets astronomers detect dark objects by the way their mass bends background starlight, and it is especially useful for finding free-floating worlds that cannot be seen directly. This is why scientists are only beginning to understand rogue planets. They are not easy to find. They do not announce themselves. They do not shine like stars. They do not transit a parent sun. Most of them simply pass through darkness without being noticed, which raises an unsettling question. How many pass near our solar system? The honest answer is, we do not know exactly. Space is enormous, and even if rogue planets are common across the galaxy, the distances between objects are still vast. A rogue planet passing directly through the inner solar system would be extremely rare, but passing through the outer reaches, far beyond Neptune, through the distant Oort cloud region, is much more plausible. Over long timescales, could one enter our solar system right now undetected? A small, dark, rogue planet in the far outer solar system could be difficult to spot, especially if it reflected little light and emitted little heat. But a large object entering the inner solar system would be much harder to hide. Its gravity would disturb other bodies. Its motion might be detected by surveys. If it were close enough and massive enough, astronomers would likely notice something unusual. So the nightmare version, a rogue planet, suddenly appearing near Earth without warning, is not realistic in the simple dramatic sense. But the deeper truth is still eerie. There may be rogue planets passing through the galaxy all around us, not close enough to threaten us, not bright enough to see, but present, hidden in the dark, and every one of them has a story. Some were born alone, some were stripped away by passing stars, Some were thrown out by giant planets during the violent youth of their solar systems. Some may have once known daylight. Some may have had oceans under a warm sun before being cast into eternal night. That is what makes their birth so tragic. They are not just planets without stars. They are worlds shaped by loss. A rogue planet is what remains after gravity breaks the relationship between a world and its sun. And from that moment on, the planet keeps going. No destination, no sunrise, no home system. Only the long, cold journey between the stars. And that is where our question becomes even more haunting. If one of these worlds is rocky, if it still has heat inside, if ice covers a hidden ocean, if there are resources beneath its frozen crust, could humans survive there? Could we build a home on a planet that the universe itself has abandoned? That is the mystery waiting in the darkness. A rogue planet does not have night. Night is something that belongs to worlds with days. On Earth, night is temporary. The sun disappears, the sky darkens, the temperature falls, and then, after a few hours, light returns. Dawn comes back. The horizon brightens. The world resets. But on a rogue planet, there is no dawn. No sunrise waiting behind the curve of the world. No morning light spilling across frozen mountains. No star rising in the sky. Only darkness. Permanent darkness. A kind of night that does not end because there is no sun to end it. That is the first and most important problem of any rogue planet. Without a parent star, there is no sunlight, no warmth from above, no natural daylight, no seasons powered by stellar energy, no golden hour, no blue sky, no shadows moving across the land. The surface would exist under the light of distant stars only, and starlight is beautiful. But it is not enough. Not enough to warm a world. Not enough to grow plants. Not enough to guide human life. If the planet has no thick atmosphere trapping heat and no strong internal energy reaching the surface, temperatures could fall far below anything humans can survive. Many exposed rogue planets could be around -200 degrees Celsius or colder. Some could be even colder, depending on their size, atmosphere, age, and internal heat. At those temperatures, the surface would not feel like winter. It would feel like a place where chemistry itself has slowed down. Water would be frozen solid. Atmospheres could collapse into frost. Oceans, if they once existed, would become sealed beneath ice. The ground would be hard, dark, and lifeless under the stars. There would be no sunlight striking the rocks, no warmth spreading across valleys, no bright side and dark side like a normal planet. The whole world would be dark. Every mountain, every crater, every frozen plain, every possible ocean beneath the crust, all of it hidden beneath an endless sky. And this darkness changes everything. On Earth, light is not just something we see by light. It's part of life itself. Plants use sunlight through photosynthesis, turning light into chemical energy. That process feeds almost every ecosystem on Earth. Even animals that never touch plants directly are still connected to sunlight through food chains. Grass grows from sunlight. Animals eat the grass. Other animals eat them. Forests rise. Oceans bloom. Crops grow. Oxygen is produced. Sunlight is not just brightness. It is the engine. On a rogue planet, surface photosynthesis would be impossible. No sunlight means no plants growing naturally on the surface. No forests. No grasslands. No algae-filled lakes beneath open skies. No agriculture without artificial lamps. No natural food chain powered from above. If life exists on such a world, it would need another energy source: geothermal heat, chemical reactions, hydrothermal vents beneath ice, something from inside the planet, not outside it. But for humans, that creates a brutal reality. A colony on a rogue planet could not depend on nature for food. It would need to manufacture light, artificial suns inside sealed habitats, rows of LED lamps over crops, power systems running constantly, every leaf growing because electricity replaces the missing star. And electricity would become survival, because without light, plants die. Without plants, food production collapses. Without food, the colony becomes dependent on stored supplies. A rogue planet would force humans to recreate an entire day-night system from scratch. Not because it is comfortable, because biology needs rhythm. The human body evolved under a star. For hundreds of thousands of years, our ancestors lived by cycles: light and dark, wake and sleep, warm and cool, morning and evening. Our brains are tied to these patterns. Deep inside us is a biological clock called the circadian rhythm. It helps regulate sleep, hormones, body temperature, digestion, alertness, mood, and countless other processes. It is not something we simply choose. It is built into us. Light tells the body when to wake. Darkness tells the body when to rest. On Earth, even before clocks, the sun gave structure to time. But on a rogue planet, there is no natural day. No sunrise to reset the brain. No sunset to prepare the body for sleep. Only whatever schedule humans create inside their habitats. And if that schedule fails, the body begins to drift. Sleep becomes unstable. Energy changes. Mood can decline. Concentration becomes harder. The immune system can weaken. Hormones can shift. Even digestion and metabolism can be affected. Permanent darkness is not just an emotional problem, it is a biological one. This is why a rogue planet colony would need artificial lighting as carefully designed as oxygen systems. The lights would not simply turn on and off. They would need to imitate Earth. Bright blue-white light in the morning, warmer light in the evening, darkness during sleep periods, gradual transitions like sunrise and sunset, separate lighting zones for work, farming, medical care, and rest. The colony would have to create time. A fake morning, a fake afternoon, a fake night, a complete artificial rhythm inside a world that has none. And this would require energy. A lot of energy. Lighting a few rooms is easy. Lighting an entire colony is not. You need lights for living spaces, lights for medical rooms, lights for tunnels, lights for repair bays, lights for emergency shelters, and most importantly, lights for agriculture. Growing food indoors requires intense, controlled lighting for many hours every day. Plants need energy, and if there is no sun, all of that energy must come from power systems. Solar panels would be useless. There is no nearby star, no daylight, no solar cycle, so the colony would need another source. Most likely, nuclear power. Fission reactors at first. Maybe fusion in a more advanced future. Possibly geothermal energy if the planet has internal heat accessible near the surface. But whatever the source, it must be constant. A rogue planet colony cannot afford long blackouts. A power failure would not only darken the rooms, it would threaten food production, heating, water systems, air circulation, communication, medical equipment, psychological stability. On Earth, when lights go out, we wait. On a rogue planet, when lights go out, the planet becomes what it always was: dark, cold, indifferent. This would shape the architecture of the colony. Habitats would be built around protected light. Living areas would glow warmly underground or beneath thick shielding. Greenhouses would become sacred places, not because they are decorative, but because they are the only places where green exists. Imagine that, a human colony on a planet with no sun. Outside, endless darkness. Inside, rows of crops growing beneath artificial lamps, a small forest of engineered light. People might gather there, not just for food, but for sanity, to see leaves, to smell plants, to remember Earth. Because psychologically, permanent darkness would be one of the hardest challenges. Humans can survive in dark environments for a time. People have lived in submarines for months. Workers spend long periods underground in mines. Scientists live in polar research stations through months of winter darkness. Cave explorers have tested how the human mind reacts without natural light. But a rogue planet would be more extreme than all of these. A submarine is still on Earth. A polar station still has Earth outside. A cave still belongs to a living planet, but a rogue planet colony would be surrounded by a darkness that is not seasonal, not temporary, not local. It is planetary. There is no outside sunrise anywhere. No warmer hemisphere. No coast under daylight. No place on the world where humans can go to stand beneath the sun. The entire planet has lost that. And for the mind, that could be heavy. At first, the stars might seem beautiful. The sky could be astonishing. Without daylight or light pollution, the Milky Way might blaze overhead with incredible clarity. Distant stars would cover the sky. Galaxies might be visible. Nebulae could stretch faintly across the darkness. But beauty does not equal comfort. A sky full of stars can still feel empty if none of them belongs to you. No star is your sun. No light warms your face. No point in the sky rises each morning to tell you the world is alive. That loneliness could shape every person living there. The colony would need psychological design as much as engineering, not just bedrooms and workstations. but light therapy rooms, virtual reality environments, artificial parks, color-rich interiors, social spaces, music, rituals, a calendar, celebrations, something to prevent time from becoming shapeless. Because without natural cycles, days can blur, weeks can lose meaning. The human mind needs markers, morning coffee, work shifts, meals, exercise, rest, community gatherings, simulated sunsets, artificial seasons. A rogue planet colony would have to invent all of this deliberately, and over generations, the question becomes deeper. Could humans adapt, not just spend a few years there, but live there long enough for children to be born, grow up, and know no other sky? A child born on a rogue planet would never experience natural sunlight unless they traveled away. Their first sunrise might be something seen only in recordings. Their idea of day would come from lamps. Their idea of outside would be darkness. Their world would be corridors, habitats, artificial farms, and star-filled skies beyond protective glass. Would they suffer from that? Or would they adapt because they never knew anything else? Maybe both. Humans are flexible. We can adjust to strange environments. We build culture around conditions. People born in deserts, forests, islands, cities, and polar regions all develop different relationships with the world around them. A rogue planet civilization might create its own relationship with darkness. They might not fear it the way Earth-born humans do. They might see the stars as normal. They might think of artificial light as home. They might build myths around the lost sun, even if their ancestors never saw it directly. But biologically, they would still need light. Their bodies would still need controlled cycles. Their eyes, brains, hormones, and sleep systems would still require careful management. Over many generations, perhaps culture could adapt faster than biology. People might become psychologically comfortable with permanent night, but their bodies would still need artificial days. That is the strange truth. Humans could survive darkness emotionally if society learned how. But physically, we would still need to bring the sun with us. Not the real sun, a manufactured one, powered by reactors, controlled by computers, protected inside walls. A colony on a rogue planet would be less like living on a surface and more like living inside a world-sized cave. A cave with no entrance to daylight. Submarines offer one comparison. A submarine is sealed, artificial, isolated, dependent on power, surrounded by an environment humans cannot enter freely. The crew lives by schedules, artificial light, machines, and discipline. But submarines eventually surface. A rogue planet does not. Deep caves offer another comparison. In caves, there is no natural light, and humans quickly lose track of time without clocks. But caves are still connected to Earth's warmth, air, water, and biology. A rogue planet colony would be more isolated, more permanent, more absolute. The darkness outside would not be a place you visit. It would be the entire world. And yet, that darkness might also become part of its beauty, because a rogue planet would show humans something no Earth sky can show. A sky without a sun, a night without interruption, the galaxy visible every hour, the stars always present, a world where the universe itself is the only horizon. And maybe, after enough time, humans would stop thinking of darkness only as absence. They might begin to think of it as environment, as home, as the condition of their world. But the first generations would struggle. They would remember blue skies, warm sunlight, clouds lit from above, the feeling of morning through a window. They would miss shadows. They would miss weather shaped by a star. They would miss the simple emotional truth that the sun is coming back tomorrow. On a rogue planet, it never does. That is why the darkness problem is not just a technical challenge. It is spiritual. It asks whether humans can live without one of the oldest comforts we have ever known. The comfort of dawn. And if we ever survive on a rogue planet, it will be because we learn to carry dawn inside our machines. Artificial light over crops. Artificial morning in sleeping quarters. Artificial sunsets in metal rooms. A human-made rhythm on a world that has no rhythm of its own. Outside, the planet remains dark, frozen, silent, moving between the stars. But inside the colony, lights turn on, plants rise toward them, people wake, work begins. And for a few hours, in a place where no sun will ever rise, humanity creates morning. A rogue planet does not receive warmth from the sky. There is no sun above it, no daylight falling on mountains, no star heating oceans, deserts, clouds, or ice. So if a rogue planet has warmth, it must come from within. That is the first strange truth. On Earth, we think of heat as something that arrives from outside. The sun warms the surface. It drives weather. It evaporates water. It feeds plants. It powers almost everything we understand as life. But planets are not only heated from above, they also carry heat inside, deep under Earth's crust, far below forests, cities, oceans, and deserts. The planet is hot. The deeper you go, the warmer it becomes. That heat comes from several sources: leftover heat from Earth's formation, pressure, and radioactive decay inside the planet's interior. A rogue planet could have something similar. Even without a star, a rocky rogue planet may still contain radioactive elements in its core and mantle. Elements like uranium, thorium, and potassium decay slowly over billions of years, releasing heat as they transform. This heat is not dramatic at the surface, but deep underground it can matter. It can keep rock warm. It can drive slow geological movement. It can melt parts of the interior. And in the right conditions, it could keep water liquid beneath ice. This is why not all rogue planets are equal. Some would be cold and dead, ancient rocky worlds that lost their heat long ago. Their surfaces would be frozen, their interiors quiet, their geology almost stopped. On those worlds, survival would be almost impossible without bringing every source of heat from outside. But other rogue planets might be different. A larger rocky planet could hold internal heat longer. A young rogue planet could still be warm from formation. A planet with a thick atmosphere could trap heat more effectively. And a gas giant rogue planet, especially one similar in size to Jupiter, could continue radiating internal heat for billions of years. Jupiter itself gives us the clue. Jupiter receives sunlight, but it also emits more heat than it receives from the sun. Part of that heat comes from the slow contraction and internal processes of the giant planet. A Jupiter-sized rogue planet floating alone between stars would not be warmed by sunlight, but it could still glow faintly in infrared, giving off heat from within. Not enough to create Earth-like daylight, not enough to make its upper atmosphere friendly, but enough to show that a world can remain thermally alive without a star. For smaller rocky rogue planets, the question becomes more difficult. How much heat is left inside? How thick is the crust? Does it have volcanic activity? Does it have water? Does it have an atmosphere? Did it once orbit a star before being ejected, or was it born alone? All of these details decide whether the planet is a frozen tomb or a hidden furnace under ice. There is also tidal heating. On worlds like Europa or Io, tidal heating happens because gravity stretches and squeezes a moon as it orbits a giant planet. That constant flexing creates internal heat. Io becomes volcanic. Europa may keep an ocean beneath its ice. But for a rogue planet, drifting alone, tidal heating is harder. If it has no star, no giant planet, and no large moon, then there is no regular gravitational stretching. A completely isolated rogue planet would not experience strong tidal heating in the same way. However, there are exceptions. A rogue planet could have a moon. If a large moon orbits it in the right way, tidal interactions could generate heat inside one or both worlds. A rogue planet could also be part of a rogue binary system, two planet-sized bodies orbiting each other in darkness. In that case, tidal heating becomes possible. Or, during rare close encounters with stars or other massive objects, gravity could disturb the planet temporarily. But those events would not provide stable long-term heat unless the planet remained bound in some kind of system. So tidal heating is possible, but not guaranteed. For most rogue planets, the more reliable source is internal heat from formation and radioactive decay. And this creates the most important distinction: a cold rogue planet versus a warm rogue planet. A cold rogue planet would have a surface colder than anything humans could survive naturally. Its atmosphere, if it had one, might collapse into frozen layers. Its water would be locked as ice. Its rocks would be still. Its interior might be too cold to offer useful geothermal energy near the surface. A warm rogue planet would be different. Still dark, still frozen at the surface, still hostile, but deep below it might hold heat. Maybe enough for geothermal gradients, maybe enough for hot springs, maybe enough to keep an underground ocean liquid. And if humans ever tried to survive on a rogue planet, this is the kind of world we would need. Not a dead wanderer, a geothermally active one. The surface might look completely lifeless. Black ice, frozen plains, mountains under starlight, no sunlight, no visible warmth. But beneath that surface, heat could rise slowly from the interior. The temperature gradient would become everything. On Earth, if you go underground, temperature generally increases with depth. The exact rate varies, but the deeper you go, the closer you get to the planet's internal heat. In some regions, geothermal energy reaches close to the surface. Iceland is one of the best examples. Iceland is cold at the surface, but geologically active beneath. It has volcanic systems, hot springs, geysers, geothermal vents, and heat that humans can use for power and warmth. People there heat homes, generate electricity, and build communities using energy from inside Earth. A warm, rogue planet would need something like that. Not identical, not Earth-like, but the same principle. A world where the sky gives nothing, but the ground gives heat. Imagine landing on a rogue planet and seeing only darkness. Your lights reveal frozen ground. The stars above are sharp and silent. There is no sunrise coming. Everything suggests death. But then instruments detect heat, a warmer region beneath the crust, a geothermal vent, a volcanic field, a crack where warm gases escape, a frozen valley where thin mist rises from underground warmth. That would be the first place humans would look, because on a rogue planet, heat is not comfort. Heat is geography. It decides where you can build, where water might exist, where energy can be extracted, where life, if it exists, might hide. A geothermally active rogue planet could have volcanic activity, though it would look different depending on the planet's chemistry. If the planet is rocky, it might have basaltic lava, volcanic plains, and heat escaping through fractures. If it is icy, it might have cryovolcanism, eruptions of water, ammonia, or other volatile materials, rather than molten rock. Hot springs could exist beneath ice. Geothermal vents could warm underground water. Subsurface oceans could remain liquid not because of sunlight, but because the planet's interior refuses to die. That is the most hopeful version of a rogue planet. Not a surface world, an underground world. The surface may be uninhabitable forever, but below the crust, conditions could improve. The deeper humans go, the warmer it becomes. At first, the upper layers would be brutally cold: ice, rock, frozen gases, and darkness. A habitat near the surface would need nuclear power and heavy insulation. But if drilling continued downward, temperatures could slowly rise. Eventually, if the planet is warm enough, there may be a depth where the surrounding rock or ice is no longer impossibly cold. A depth where heating systems need less power. A depth where liquid water might exist naturally. A depth where geothermal energy can be tapped directly. That depth could vary enormously. On one planet, useful warmth might be only a few kilometers down. On another, it could be tens of kilometers. On a cold, dead, rogue planet, it might be unreachable. This is why choosing the right rogue planet matters more than landing anywhere. Humans would not search for a flat surface first. They would search for heat, thermal anomalies, volcanic regions, geological fractures, subsurface ocean signatures, magnetic clues, chemical vents. A rogue planet colony would almost certainly be underground, near a geothermal zone. It might begin as a small base drilled into frozen crust. Robots would excavate tunnels. Nuclear reactors would provide early power. Then, slowly, the colony would tap into the planet's own heat. Geothermal wells could bring warm fluids upward. Heat exchangers could warm habitats. Steam or hot liquids could drive turbines. If conditions allow, thermal energy could melt ice into water. It could support underground agriculture. It could reduce dependence on imported fuel. And in the long term, it could make survival sustainable. This is the dream scenario. A rogue planet with internal heat strong enough to power human life. A starless world where the surface is frozen, but the underground becomes habitable through engineering, not comfortable, not natural, but possible. The colony would not live under open skies. It would live beneath the crust, tunnels carved into rock or ice, pressure-sealed chambers, artificial lights, greenhouses warmed by geothermal energy, water extracted from melted ice, power drawn from the planet's interior. Above them, the surface remains dark. No sun, no dawn, only stars. But below, humans create warmth from the planet's hidden fire. There is something almost poetic about that. On Earth, life began and flourished under sunlight. But even here, not all life depends directly on the sun. Deep in the oceans, around hydrothermal vents, entire ecosystems survive using chemical energy from Earth's interior. No sunlight reaches them, yet life exists there. That tells us something important. A world without sunlight is not automatically a world without energy. Energy can come from below, from rock, from chemistry, from heat, and if nature can use that energy, maybe humans could too. But the challenge would be enormous. Drilling deep underground on a rogue planet would be difficult. Machines would need to function in extreme cold. Shafts would need to be stabilized. Heat systems would need to prevent freezing. The deeper the colony goes, the more pressure and geological stress it may face. And if the planet is geologically active, that creates another danger. Volcanoes provide heat, but also instability. Earthquakes, gas releases, toxic chemistry, ground movement. A colony near geothermal energy must balance safety and access. Too far away, and the heat becomes useless. Too close, and the environment becomes dangerous. This is why early exploration would rely heavily on robots. They would map heat flow, drill test holes, analyze gases, measure seismic activity, search for underground water, identify stable zones. Humans would only arrive after the planet's internal behavior was understood well enough to risk a base, because on a rogue planet, a bad landing site could mean death. Not quickly, maybe, but slowly, through energy loss, through freezing systems, through failed drilling, through lack of water, through choosing a place where the planet gives nothing back. The heat problem is really the survival problem. Without sunlight, every colony must answer one question. Where does the energy come from? Nuclear power could keep humans alive for a time. Fusion, if available, could change everything. But if the colony wants to last for generations, it needs local energy. On a rogue planet, that means geothermal heat. The planet's own warmth becomes the replacement for a star, not a bright star in the sky, a hidden star below the ground, a buried source of survival. So the best rogue planet for humans would not be the one with the most beautiful surface. There may be no beautiful surface in the normal sense. The best rogue planet would be the one with heat beneath it, a warm core, a thick, insulating crust, possible liquid water underground, geothermal vents, maybe volcanic activity, maybe subsurface oceans, a world that looks dead from space but is still alive inside. And if humans ever found such a world, the first colony would not celebrate the sky. It would celebrate the ground. The moment instruments detect heat rising from below, the moment drills reach warm rock, the moment frozen water becomes liquid, the moment the planet itself begins to help keep humans alive. That is when a rogue planet stops being only a wandering tomb. It becomes a possible home, a dark home, a dangerous home, a home without sunrise, but a home with warmth hidden beneath the ice. And in the endless night between the stars, that hidden warmth may be the difference between impossibility and survival. A rogue planet may be dark. It may be cold. It may be drifting alone between the stars. But that does not automatically mean it is airless. And this is one of the strangest possibilities of all. Because when we imagine a planet without a star, we usually picture a frozen dead rock exposed to space, a surface covered in ice, a sky filled only with stars, no clouds, no pressure, no weather, nothing moving except dust and darkness. But some rogue planets may still have atmospheres, and in some cases, those atmospheres could be enormous, thick, deep, heavy enough to change the entire fate of the world. The first question is simple. Does a rogue planet have an atmosphere? The answer depends on the planet. Some rogue planets may lose their atmospheres during the violent event that ejects them from their solar system. A close encounter with a giant planet, a powerful gravitational slingshot, or intense radiation from a young star could strip away part of the gas surrounding them. Small rocky worlds are especially vulnerable. If a planet is too small, its gravity may not hold on to light gases for billions of years. If it is exposed to strong stellar radiation before being ejected, its atmosphere may already be weakened. And once it drifts into the cold of interstellar space, some gases may freeze out and collapse onto the surface. But larger rogue planets are different. A massive rocky world, a super-Earth, or a gas giant wanderer could hold on to an atmosphere for an incredibly long time. And, strangely, being far from a star may help. Around a normal star, planets are constantly exposed to solar wind, streams of charged particles flowing outward from the star. Over millions or billions of years, that solar wind can erode atmospheres, especially if the planet has weak magnetic protection. Mars is one of the clearest warnings. It once had a thicker atmosphere, but without a strong global magnetic field, much of it was stripped away over time. A rogue planet, drifting far from any star, does not face the same constant attack. No nearby solar wind, no intense ultraviolet light from a parent star, no stellar storms constantly blasting the upper atmosphere. In deep space, the atmosphere may be cold, but it may also be protected from the violence of a star. That means some rogue planets could retain thick atmospheres for billions of years, not because they are warm, but because nothing nearby is stripping them away. And that changes the entire survival question, because an atmosphere is not only air. An atmosphere is insulation. It is pressure. It is protection. It can trap heat. It can slow heat loss. It can make the difference between a surface that is completely frozen and the surface that remains just warm enough for strange possibilities. The most powerful example is a thick hydrogen atmosphere. Hydrogen is the lightest gas, and small planets struggle to hold on to it. But a massive rogue planet, especially a super-Earth, might keep a thick layer of hydrogen around it. And hydrogen can act like an insulating blanket. If the planet still produces internal heat from radioactive decay or leftover formation energy, a thick hydrogen atmosphere could trap some of that heat near the surface. This does not mean the planet becomes Earth-like. There would still be no sunlight, no blue sky, no natural photosynthesis, no day, but the surface could be warmer than expected. In some models, a rogue planet with a thick enough hydrogen atmosphere could keep liquid water at the surface or beneath an ice layer, even without a star. That idea feels almost impossible. A world with no sun, but still warm enough for liquid water, because its own atmosphere traps the heat rising from inside. It would be like a planet wrapped in darkness, carrying its warmth under a deep, invisible blanket. But there is a major difference between a survivable atmosphere and a breathable one. This is where humans must be careful. An atmosphere may keep pressure. It may reduce temperature extremes. It may allow sound to travel. But that does not mean humans can breathe it. A hydrogen atmosphere could help keep a planet warm, but it would not support human lungs. A methane atmosphere might be thick, but unbreathable. A carbon dioxide atmosphere could provide pressure, but become deadly without oxygen. A nitrogen atmosphere might feel closer to Earth's, but without oxygen, it would still be useless to breathe. For humans, breathable air means a very specific mixture. Enough oxygen, not too much carbon dioxide. Pressure within a survivable range. No toxic gases at dangerous concentrations. A stable temperature, no extreme chemical hazards. That combination is rare, very rare. A rogue planet could have an atmosphere that helps machines survive while still being deadly to humans. So astronauts would almost certainly need breathing apparatus. At minimum, they would need oxygen supplies. If the pressure outside was safe, they might not need a full pressure suit in the way they would on the moon. But they would still need sealed breathing systems, filters, thermal protection, and chemical sensors. If the pressure was too low, they would need full pressure suits. If the pressure was too high, they would need protective equipment designed more like deep diving systems. If the atmosphere was toxic or chemically reactive, the suit would need to keep every part of the body isolated. The atmosphere could help, but it could also become another danger. A rogue planet's atmospheric chemistry would depend heavily on its origin. A planet ejected from a young solar system might carry the atmosphere it formed with. A rocky world could have nitrogen, carbon dioxide, water vapor, methane, ammonia, or sulfur compounds. A gas giant rogue would be dominated by hydrogen and helium. An icy rogue planet might have methane, nitrogen, or carbon monoxide frozen into surface layers, with some gases released by internal heat. Without a star, atmospheric chemistry changes. On Earth, sunlight drives much of atmospheric chemistry. Ultraviolet light breaks molecules apart. Heat creates circulation. Seasons move gases and moisture. Photosynthesis changes oxygen levels. Weather cycles constantly reshape the atmosphere. On a rogue planet, none of that happens in the same way. There is no sunlight powering ordinary weather, no photosynthesis filling the air with oxygen, no warm ocean evaporating under a star. Chemistry becomes slower, darker, driven by internal heat, cosmic rays, radioactive decay, volcanic gases, geothermal vents, and perhaps lightning or chemical reactions deep in the atmosphere. If the planet has volcanic activity, gases could escape from the interior. Carbon dioxide, water vapor, sulfur dioxide, methane, hydrogen, ammonia. These gases could build an atmosphere over time or replenish one that would otherwise freeze or escape. But many of them are dangerous. A rogue planet atmosphere might be thick and protective, but filled with gases humans cannot survive. Carbon monoxide, hydrogen sulfide, ammonia, methane, sulfur compounds, too much carbon dioxide, too little oxygen. A sky can be beautiful and still deadly. That is one of the central lessons of space exploration. Human survival does not only require an atmosphere, it requires the right atmosphere. And pressure matters too. On Earth, atmospheric pressure at sea level gives our bodies the environment they need. It keeps fluids stable. It lets lungs work properly. It allows oxygen to enter the blood. If pressure is too low, the body cannot function without protection. If pressure is too high, breathing becomes difficult and gases can become toxic, depending on the mix. So a rogue planet colony would first ask 3 questions. Is there pressure? Is there oxygen? Is the atmosphere chemically safe? Most of the time, the answer to at least one of those would be no. And that means humans would live inside sealed habitats. Even on a rogue planet with a thick atmosphere, the colony would likely remain enclosed. Airlocks, breathing systems, atmospheric processes, gas analyzers, emergency shelters. The outside air might be useful industrially, but not biologically. If the atmosphere contained nitrogen, that could be valuable. Nitrogen can help create breathable air mixtures inside habitats. It can also support agriculture. If the atmosphere contained carbon dioxide, plants could use it under controlled conditions. If it contained hydrogen, it could be used in fuel systems or chemical production. So even an unbreathable atmosphere could become a resource. A dangerous resource, but still a resource. Could a rogue planet have a nitrogen-oxygen atmosphere like Earth? In theory, maybe, but in practice, it would be extremely unlikely. Earth's oxygen-rich atmosphere exists largely because of life. For billions of years, organisms changed our atmosphere by producing oxygen through photosynthesis. Without biology, free oxygen usually reacts with rocks, volcanic gases, and surface materials. It does not easily remain abundant. A rogue planet without sunlight would not have surface photosynthesis. So if it had oxygen, it would need another source. Maybe ancient life from before ejection. Maybe chemical reactions involving ice and radiation. Maybe unusual geochemistry. But an Earth-like oxygen atmosphere on a rogue planet would be extraordinary. Not impossible in imagination, but not something we should expect. And if we found one, it would be one of the most shocking discoveries in astronomy. Because oxygen in an atmosphere can be a sign that something unusual is happening. Maybe life, maybe powerful chemistry, maybe a history unlike anything we know. But for a human mission, we could not assume that luck. We would bring our own air, or make it. A colony could extract oxygen from water ice, if available. It could split water into hydrogen and oxygen using electricity. It could process carbon dioxide. It could grow plants under artificial light. It could recycle air in closed life support systems. The atmosphere outside might help provide raw materials, but the breathable environment would be created inside. And then comes the bigger question. Could we terraform a rogue planet? Could we modify its atmosphere and make it human-friendly? The answer is almost certainly not on any short human timescale. Terraforming is already an enormous challenge on Mars. And Mars at least has sunlight. A rogue planet has none. To make its atmosphere breathable, humans would need to change its pressure, chemistry, temperature, and energy balance. If the planet is too cold, gases may freeze. If there is no oxygen, it must be produced in massive quantities. If the atmosphere is toxic, it must be removed or transformed. If there is no sunlight, photosynthesis must be artificially powered. And if the planet lacks enough internal heat, the atmosphere may never become stable in the way we want. Terraforming a rogue planet would require energy on a scale almost impossible to imagine. Not years, not decades, maybe thousands of years, maybe longer. It would be less like engineering a habitat and more like rewriting an entire world. A more realistic approach would be paraterraforming. Instead of transforming the whole planet, humans would build enclosed regions, domes, underground cities, sealed valleys, pressurized caverns, habitats where the atmosphere is controlled locally. Outside remains hostile. Inside becomes livable. That is much more realistic. On a rogue planet, humanity would not terraform the world at first. We would carve small islands of breath into it, warm rooms beneath frozen ground, greenhouses under artificial light, air recycled again and again. A human atmosphere made inside machines. And perhaps, after centuries, those enclosed habitats could expand. Tunnel networks, subsurface cities, artificial ecosystems, large pressurized chambers, but the open surface would remain dark and alien. The possibility of finding a rogue planet with Earth-like air is one of the most tempting ideas. Imagine a world with no star, but a breathable atmosphere. A planet drifting through darkness, somehow holding oxygen, nitrogen, pressure, and maybe even warmth beneath clouds. It would feel almost mythical, but scientifically, we should be careful. A truly Earth-like rogue planet would likely require an extraordinary history. Maybe it was ejected recently, before its atmosphere froze or changed too much. Maybe it has intense internal heat. Maybe it has a thick greenhouse atmosphere. Maybe it has underground life-producing gases. Maybe it was once a living world under a star and still carries the chemical memory of that life. If such a planet existed, it would be one of the most important discoveries ever made. But for survival planning, humans would not count on it. We would assume the atmosphere is either absent, unbreathable, toxic, too cold, too dense, too thin, or chemically unstable. And we would build accordingly. That is the truth of the atmosphere question. A rogue planet may have air. It may even have thick air. That atmosphere may protect it, insulate it, preserve heat, carry sound, hold clouds, maybe even support exotic chemistry. But for humans, air is not enough. We need the right air, and in the darkness between stars, the right air may be almost impossible to find. So if humans ever survive on a rogue planet, they will not simply step outside and breathe. They will carry Earth with them. In tanks, in pipes, in greenhouses, in sealed habitats, in carefully balanced systems that turn water, energy, and chemistry into every breath. Outside, the rogue planet's atmosphere may be thick, strange, and ancient. It may press against the walls. It may whisper over frozen plains. It may trap heat from a hidden core. But inside the colony, humans will breathe an atmosphere made by design. A small pocket of Earth air floating on a planet that has no sun. A rogue planet may look like the last place in the universe where water could exist. No sunlight, no warmth from a star, no clouds glowing under daylight, no rivers reflecting a sky, only darkness. A frozen world drifting between stars. At first, the answer seems obvious. Water should be impossible there. If a planet has no sun, then any ocean on its surface should freeze. Any lake should become stone. Any river should stop forever. The surface should become a locked shell of ice, harder than rock, colder than anything humans could touch. And on many rogue planets, that is probably true. Surface water would be frozen solid, not a thin layer of frost, not a winter lake waiting for spring, but deep, ancient ice. Ice that may have existed for millions or billions of years without ever melting under sunlight. There would be no warm season, no equator receiving daylight, no summer thaw, no rainstorm returning water to the surface. The entire planet would be trapped in a permanent freeze. And yet, water may still be there. That is the strange part. A rogue planet does not need sunlight to contain water. It only needs to have formed with it, or collected it, or preserved it, or hidden it deep enough underground. Because water is not rare in the universe, it exists in comets, in icy moons, in planetary crusts, in frozen grains, between stars, in the outer regions of solar systems. A rogue planet could carry enormous amounts of water, especially if it formed far from its original star, beyond the snow line, where ice was abundant. The problem is not whether water exists. The problem is where it is, and in what form. On the surface, it would almost certainly be frozen. But below the surface, the story could change. If the rogue planet has internal heat, that heat could warm the deeper layers. Radioactive decay in the core, leftover heat from formation, pressure, and geothermal activity could create a temperature gradient. The deeper you go, the warmer it becomes. At the surface, the world may be colder than -200 degrees Celsius, a place of hard ice and endless night. But several kilometers down, the temperature may rise. Deeper still, ice may soften, and if conditions are right, liquid water may exist, hidden beneath a frozen crust. A subsurface ocean. This is one of the most important possibilities for warm rogue planets. A planet could be dead on the outside, but wet on the inside. A world with no star, no daylight, no photosynthesis, and no surface warmth could still have a buried ocean heated from below. That ocean would be completely dark. No sunlight would ever reach it. No blue waves, no open sky, no reflection, just liquid water trapped between ice above and the warmer rock below. But scientifically, that kind of environment matters, because on Earth, life exists in deep oceans, caves, and hydrothermal vent systems where sunlight never reaches. Those ecosystems depend on chemistry and heat from the planet itself. So a rogue planet with a subsurface ocean would not be automatically lifeless. It would be one of the most mysterious environments imaginable. For humans, however, a hidden ocean creates a brutal practical question. How do you reach it? If water is locked beneath kilometers of ice, survival becomes an engineering challenge. A colony cannot simply walk outside and collect water from a stream. There are no streams, no lakes, no rain, only frozen material, possibly buried ocean layers, and ice so cold it behaves like stone. The first source humans would use would probably be surface ice. If the surface contains water ice, robots could mine it, cut it, crush it, melt it, and purify it. This sounds simple, but on a rogue planet, even simple actions become difficult. The ice may be extremely cold and hard. Machines may become brittle. Drills may freeze. Power cables may crack. Melting ice requires heat. Heat requires energy. Energy must come from nuclear reactors, geothermal systems, or some advanced power source. Nothing is free. Every liter of water would cost power. Every tank would need to be protected from freezing again. A colony would need heated processing rooms, insulated storage tanks, pumps, filters, and emergency reserves. Raw ice would enter the system as frozen material. Then it would be melted, filtered, chemically tested, purified, sterilized, stored, recycled, used, and used again. Because on a rogue planet, wasting water would be unacceptable. Water would become one of the most protected resources in the colony, not because the planet has none, but because accessing it is hard. If the colony needed deeper liquid water, the challenge becomes far greater. Drilling through kilometers of ice would require industrial-scale technology. Mechanical drills could cut downward, but they would need constant maintenance and huge amounts of power. Thermal drills could melt their way through the ice, using heated probes to descend slowly into the crust. A cryobot could be used, a robotic melting probe designed to sink through ice while sending data and possibly maintaining a communication cable back to the surface. But a rogue planet makes this harder than an icy moon in a solar system. There is no solar power, no easy resupply, no nearby mission control. Every system must work in darkness, extreme cold, and isolation. The drill would need to keep its own path from refreezing or create a protected shaft. It would need to avoid contamination. If scientists are searching for native life, it would need to survive pressure, ice movement, possible chemical impurities, and unknown geology. And if the hidden ocean lies tens of kilometers deep, the project becomes one of the hardest things humans have ever attempted. But reaching that water could change everything. A subsurface ocean would provide more than drinking water. It could provide oxygen, industrial chemistry, maybe even geothermal energy if it connects to warm rock below. Water could be split by electrolysis into oxygen and hydrogen. Oxygen would support breathing. Hydrogen could be used for fuel, chemical processing, or energy storage. Water could cool reactors, grow food, support hygiene, shield against radiation, maintain pressure systems. In space survival, water is not only water, it is life support, it is fuel, it is protection, it is agriculture, it is the foundation of a colony. There may be other water sources too. A rogue planet traveling through interstellar space may encounter debris over enormous timescales. Comets, asteroids, icy bodies, dust, fragments left over from star systems. Most encounters would be rare because space is vast, but over billions of years, a rogue planet could collect impacts from icy objects. Some of that material may become trapped on the surface. Comets and asteroids could deliver water, ice, and other volatiles. Each impact would be violent, but over long periods, those impacts could add material to the crust. In some cases, they may create buried layers of ice mixed with dust, organics, and minerals. A human colony might search impact regions for accessible ice deposits, places where frozen material from ancient collisions collected near the surface. The planet's atmosphere, if it has one, could also matter. If the rogue planet has a hydrogen-rich atmosphere, that atmosphere might help preserve heat, but it could also become part of water chemistry. Hydrogen itself is not water, but if oxygen-bearing materials exist in the crust or mantle, chemical reactions could produce water or preserve water compounds. A thick atmosphere might also trap water vapor deep in lower layers, or allow exotic weather patterns depending on pressure and temperature. But on a cold rogue planet, the water cycle would not look like Earth's. There would be no ocean evaporating under sunlight, no clouds forming from solar heating, no rain falling into rivers. Instead, the water cycle would be slow, dark, and mostly geological. Ice sublimating in tiny amounts, frozen particles drifting in the upper atmosphere, volcanic or geothermal vents releasing vapor, water freezing back onto the surface, subsurface melt moving through cracks, ice layers slowly deforming over time. If the planet has an atmosphere, there could even be frozen precipitation, not warm rain, not snow in the Earth sense, but tiny frozen particles falling through dark air, a silent rain of ice crystals or frozen chemical grains, descending under starlight onto a surface that never thaws. Imagine standing outside the colony in a heated suit. The sky is black, the stars are sharp, there is no sun, and around your lights, tiny frozen particles drift downward from the atmosphere. Not rain, not snow, something colder, a weather system without daylight, a water cycle without warmth. That is what a rogue planet might offer. A world where water moves, but slowly. A world where ice dominates everything. A world where liquid water, if it exists, hides deep below. For a human colony, water recycling would be essential from the first day. Even if ice is available, the colony cannot waste energy mining and melting endlessly. Every drop must be reused. Water from breath, sweat, urine, washing, cooking, agriculture, industrial systems. All of it would be captured, filtered, cleaned, and returned to use. The colony would need systems similar to those used on space stations, but far more robust and long-lasting. A space station can receive supplies. A rogue planet colony cannot depend on that. A small human crew may need dozens of liters of water per person per day when all uses are counted. Drinking, food preparation, hygiene, agriculture, oxygen production, and system maintenance. A larger colony would need thousands of liters daily. And if farming is included, the demand grows dramatically. Hydroponic farms can recycle water efficiently, but they still require reservoirs, nutrient solutions, humidity control, and constant monitoring. A leak in the water system would be serious. A contamination event could be dangerous. A frozen pipe could shut down entire sections of the colony. Water would need to be stored in multiple protected locations, not one tank. Many backup reserves, emergency ice stockpiles, underground reservoirs, recycling loops, portable supply units. Water would become part of the colony's architecture. Walls lined with water tanks for radiation shielding. Greenhouses built around water recovery systems. Living quarters designed to capture humidity. Industrial zones separated to prevent contamination. Everything connected, nothing wasted. And here lies the great irony of a rogue planet. It may be water-rich and still feel like a desert. A planet could contain oceans worth of water, but if that water is frozen into a crust 50 kilometers thick, it is not immediately useful. A world could have more water than Earth and still offer none freely. No rivers, no lakes, no rain that humans can drink, only ice, only hidden oceans, only locked resources. That is one of the deepest lessons of survival beyond Earth. A resource is not valuable simply because it exists. It becomes valuable only when you can reach it, process it, and use it safely. A rogue planet might hold water everywhere. In its crust, in its atmosphere, in buried oceans, in ancient impact deposits. But humans would have to fight for every drop, drill for it, melt it, filter it, protect it, recycle it. And if they succeeded, water would become the first sign that survival might be possible. Not easy, not natural, but possible. The moment a colony extracts clean water from the frozen crust of a rogue planet would be historic, because it would mean humans had taken a world of darkness, a world with no sun, a world locked in ice, and found the one thing life needs most: a clear tank of liquid water glowing under artificial light, surrounded by machines, protected from freezing, ready to become air, food, heat, and survival. Outside, the planet remains dark. The surface stays frozen. No river flows beneath the stars. No ocean reflects the sunrise. But inside the colony, water moves again. Through pipes, through roots, through human bodies, through a closed system built against the dark. And in that small artificial cycle, on a planet where nature froze everything solid, life begins to continue. On a rogue planet, energy is not part of life. Energy is life. There is no sun to help you, no daylight falling on solar panels, no warm afternoon, no seasonal cycle that brings heat back after winter. A rogue planet gives nothing from above. If humans ever build a colony there, every light, every breath, every liter of melted water, every warm room, every medical device, every greenhouse, every communication signal, and every machine keeping people alive would depend on one question: where does the power come from? On Earth, energy surrounds us so completely that we almost forget it exists. The sun warms the surface. Plants turn sunlight into food. Winds are driven by solar heating. Rain falls because sunlight powers the water cycle. Even fossil fuels are ancient sunlight stored in chemical form. But on a rogue planet, the entire solar foundation disappears. Solar power would be completely useless. Not weak, not inefficient. Useless. A planet drifting between stars receives no meaningful sunlight from a nearby star. The distant stars in the sky may be beautiful, but their combined light would be far too faint to power a colony. You could cover entire valleys with solar panels and still receive almost nothing compared to Earth. There is no sunrise to recharge the system, no daytime energy peak, no solar farm, no backup from the sky. So the first human colony on a rogue planet would have to bring its own star. Not literally, but in the form of nuclear energy. Nuclear fission would almost certainly be the primary energy source at the beginning. Fission is powerful because it does not need sunlight, wind, or weather. It does not care whether the planet has a day or night. It can run underground, inside shielded structures, producing steady heat and electricity for years. That is exactly what a rogue planet colony would need. A constant source, a dependable source, a source that does not vanish when clouds form, or when the world rotates, or when the surface freezes. Compact nuclear reactors would become the heart of the colony. One reactor for the main habitat, one reactor for life support and water systems, one reactor for agriculture, one reactor kept as backup, smaller emergency generators placed in survival shelters. The colony would not trust one machine. It could not, because if the main energy system fails, the problem does not remain electrical, it becomes biological. The lights go out, the heaters slow down, the water processing system stops, the air circulation weakens, the greenhouse begins to die, the communication system loses power, the temperature inside the habitat starts dropping. On Earth, a blackout is an emergency. On a rogue planet, a blackout is the beginning of extinction. That is why nuclear fission would be so valuable. A small amount of nuclear fuel can produce enormous amounts of energy. Compared to chemical fuel, it is incredibly energy dense. A colony could bring enough fuel to operate for years, perhaps decades, depending on the reactor design, the size of the crew, and how much industry the settlement needs to support. But the fuel question would still be serious. A small science outpost might survive on several compact reactors and carefully ration fuel. A larger colony with agriculture, drilling, manufacturing, water extraction, hospitals, laboratories, transportation, and full life support redundancy would need far more. The energy budget would be huge. Heating alone would consume power continuously. The outside world may be -200 degrees Celsius or colder. Every habitat wall would leak heat into the surrounding darkness, even if the colony is buried underground, even if it is insulated carefully. Heat loss never stops. Then comes lighting. Humans need artificial day-night cycles. Plants need grow lights. Work areas need illumination. Medical rooms need stable power. Greenhouses need intense light for hours every day. A rogue planet colony must create all the light that the missing sun never provides. That means agriculture becomes one of the largest energy demands. Growing food without sunlight is possible, but expensive. Every calorie of food begins as electricity. LED systems must run constantly. Pumps must circulate water. Nutrients must be balanced. Humidity must be controlled. Air must be filtered. Waste must be recycled. Food is not grown by nature. It is grown by power. Water systems need power too. Ice must be mined, cut, melted, purified, stored, and pumped. If the colony drills towards subsurface water, the energy demand becomes even larger. Deep drilling requires motors, heat, pressure systems, sensors, and repair robots. And once the water is extracted, it must never freeze again. So it needs heated tanks, insulated pipes, backup circulation loops, power everywhere. Then there is air. Oxygen must be produced or recycled. Carbon dioxide must be removed. Air pressure must be maintained. Filters must run. Pumps must circulate atmosphere through every room and tunnel. Without power, air becomes dangerous. Slowly at first, then quickly. This is why the energy budget of a self-sustaining rogue planet colony would be planned with extreme care. Not only how much energy is needed on a normal day, but how much is needed during emergencies. What if a drill jams underground? What if a reactor goes offline? What if a greenhouse disease forces crops to be replaced? What if a section of the habitat loses heat? What if communication arrays need more power to reach a distant relay? Every system needs margins, extra capacity, reserve power, backup power, emergency power. A colony that runs at the edge of its energy limit is already dying. At first, all nuclear fuel would have to be brought from elsewhere. That makes the early colony dependent. Even if it can mine ice and grow food, it cannot truly survive forever if its fuel supply is limited. A fission-powered colony might last decades with enough fuel, but eventually the question returns: what happens when the fuel runs low? This is where the transition to local energy becomes essential. The dream source is fusion. Fusion power would change everything. Instead of relying on heavy fission fuel shipped from Earth or another base, a colony with advanced fusion could use lighter elements as fuel. If the planet has hydrogen-rich materials, deuterium, or accessible water ice that can be processed, fusion could provide long-term energy at a scale fission may struggle to match. Fusion is the dream energy source for rogue survival because it offers the possibility of enormous power without needing a star. A human-made star in a chamber, contained, controlled, running underground. If humans ever master reliable compact fusion, rogue planets become far more realistic as homes. The colony could power massive greenhouses, deep drilling systems, industrial manufacturing, heating networks, transport vehicles, and scientific stations. But fusion is not something to assume for the first generation. It may be the future, not the beginning. Fission keeps people alive. Fusion, one day, might let them expand. But even fusion is not the only possibility. The rogue planet itself may provide energy. Geothermal energy could become the most important local source if the planet is warm inside. A rogue planet with a hot core, radioactive decay, volcanic activity, or subsurface oceans may leak heat upward through the crust. Humans could drill into that heat and harvest it. This is one of the best survival scenarios because geothermal energy is local. It does not need sunlight. It does not need imported fuel forever. It comes from the planet. If the colony can tap it safely, geothermal power could heat habitats, melt ice, generate electricity, and support agriculture. The process might work through deep wells, drill into warm rock, pump fluid down, let the planet heat it, bring it back up, use the heat to drive turbines, or warm the colony directly. On Earth, places like Iceland already use geothermal energy for heating and electricity. A rogue planet colony would use the same principle but under far more extreme conditions. There would be no comfortable surface town, no daylight, no natural rivers, only machines tapping heat from below, while the surface above remains frozen in permanent night. But geothermal energy comes with challenges. The heat must be close enough to reach. The rock must be stable. The drilling must be reliable. The fluids must not freeze in pipes. The system must survive quakes, pressure changes, mineral buildup, and corrosion. If the planet is volcanically active, that is both a gift and a danger. Volcanoes mean heat, but they also mean instability. A colony would need to be near enough to access warmth, but far enough to avoid eruptions, toxic gases, earthquakes, and collapsing ground. Energy on a rogue planet would always be a balance between opportunity and risk. Wind power is another possibility, but only under specific conditions. If the rogue planet has a thick atmosphere and active weather, winds could move across the surface. If the atmosphere is dense enough, even slow winds might carry useful energy. Turbines could be placed in windy corridors, pressure gradients, or near geothermal regions, where heat creates atmospheric movement. But wind is unreliable unless the planet has a stable circulation system. Without solar heating, normal weather patterns may be weaker or very different from Earth's. Some rogue planets may have almost no wind. Others with thick atmospheres and internal heat may have strange, slow, powerful circulation. If wind exists, it could help, but it would not be the main source. Not at first. A rogue colony cannot depend on weather it does not fully understand. Wind could charge storage systems, support surface stations, run auxiliary equipment, but the colony's survival would still depend on nuclear and geothermal power. Energy storage would be critical. Even if the reactors run well, even if geothermal systems work, the colony needs reserves, batteries, thermal storage, hydrogen fuel, flywheels, compressed gases, heated underground reservoirs, emergency power cells, stored chemical energy. A good colony would not only produce energy, it would store it in many forms. Electricity for immediate use, heat stored in insulated masses or fluid tanks, hydrogen and oxygen stored for fuel cells, backup batteries in each module, independent emergency packs in survival shelters, because power failures do not always happen everywhere at once. A section of the colony could lose connection. A tunnel could be damaged. A reactor line could fail. A battery bank could malfunction. So every important part of the base must survive temporarily on its own. The medical bay needs independent power. The command center needs independent power. The greenhouse needs emergency lighting. The air system needs backup pumps. The water tanks need freeze protection. The shelters need enough energy to keep people alive for days or weeks. Redundancy is not luxury. It is the key to survival. And the reason is cascading failure. On a rogue planet, systems are connected. If power fails, heating fails. If heating fails, pipes freeze. If pipes freeze, water stops. If water stops, oxygen production may stop. If oxygen production stops, air reserves begin falling. If lights fail, crops die. If crops die, food production collapses. If communication fails, the colony loses contact. If medical systems fail, injuries become harder to treat. One failure becomes two. Two become five. Five become collapse. That is the nightmare scenario. Not an explosion. Not one dramatic disaster. A slow chain reaction. A colony freezing from the inside because its energy spine broke. This is why the entire settlement would be designed like a living organism with multiple hearts, several reactors, multiple power grids, isolated circuits, emergency shelters, manual overrides, robotic repair units, spare parts, fuel reserves, local geothermal backup, energy storage everywhere. The colony would constantly monitor its own power, like a body monitoring its heartbeat. How much energy is being produced? How much is being stored? Which systems are using too much? Which reactor is aging? Which battery is degrading? Which greenhouse can reduce lighting without losing crops? Which habitats can be sealed to save heat? Survival would become mathematics. Every system prioritized. In an emergency, the colony might enter survival mode. Lights dim. Non-essential laboratories shut down. Greenhouse cycles reduce. Manufacturing stops. Surface missions cancel. People gather in central warm zones. The colony shrinks itself temporarily, protecting the core systems first. Air, heat, water, medical care, communication, food preservation. Everything else waits. This would be frightening, but it would also be planned. A serious rogue planet colony would practice power loss drills constantly, because one day something will fail. The difference between survival and death is whether the failure was expected. Over time, if the colony succeeds, its energy system would evolve. At first, imported fission reactors keep it alive. Then geothermal wells reduce the load. Then more local systems come online. Wind turbines, if useful, support secondary networks. Energy storage expands. Manufacturing begins producing replacement parts locally. If fusion becomes available, the colony transforms. It can grow. More light, more food, more heat, more industry, more people. The colony moves from survival to permanence. But until that day, the truth remains simple. On a rogue planet, energy is the replacement for the sun, not just for warmth, for time, for food, for air, for hope. The planet itself gives no daylight. The sky offers no help. The stars are too far away to matter. So humans must build their own sunrise underground. A reactor turns on. Lights glow across the habitat. Water begins moving through pipes. Air circulates. Plants open under artificial lamps. People wake in rooms where morning is not natural, but created. Outside, the rogue planet remains dark, frozen, silent, a world without a star. But inside the colony, energy flows, and as long as it flows, human life continues. On a rogue planet, food does not begin with soil. It begins with electricity. There is no sunlight falling on fields. No warm season, no rain cycle, no open sky where plants can grow. There is only darkness, and in that darkness, every calorie must be manufactured. That is the brutal truth of food on a rogue planet. On Earth, agriculture feels natural because the sun does most of the work. It powers photosynthesis. It drives the water cycle. It warms the soil. It gives plants the energy they need to turn carbon dioxide, water, and minerals into leaves, roots, fruits, grains, and seeds. But on a rogue planet, there is no sun, no daylight, no photosynthesis on the surface, no wheat fields, no forests, no fruit trees, no natural farms. The surface would be frozen and dark, perhaps colder than -200 degrees Celsius, with no light strong enough to grow anything. Even if the planet had water, it would likely be locked as ice. Even if it had an atmosphere, it would probably be unbreathable or chemically strange. So humans would not farm the surface. They would farm underground, deep inside sealed habitats, beneath rock or ice, where temperature, air, water, pressure, nutrients, and light could be controlled. A rogue planet farm would not look like a farm. It would look like a machine. Rows of stacked trays, pipes carrying nutrient water, LED lights glowing above leaves, sensors measuring every drop, robots trimming roots and checking for disease, air pumps moving carbon dioxide and oxygen through closed chambers. This would be hydroponic agriculture. Plants grown without soil, using nutrient-rich water instead. Hydroponics would be essential because soil is heavy, messy, unpredictable, and difficult to manage in a closed world. Nutrient solutions can be controlled precisely. Water can be recycled. Crops can be stacked vertically. The farm can be sealed, monitored, and protected. But there is one problem: light. On Earth, sunlight is free. On a rogue planet, light must be paid for with energy. Every leaf would grow under artificial lamps. Every potato, every grain, every vegetable, every algae tank. The colony would need to create an artificial sun, and that sun would run on nuclear power, geothermal energy, or fusion if humanity ever masters it. This makes food expensive, not in money, in energy. Every calorie grown underground would require electricity first. The colony would have to decide carefully which crops are worth growing. Leafy greens are useful for vitamins and morale, but they do not provide enough calories. Wheat, potatoes, soybeans, and other calorie crops require more time, space, water, and light. A self-sustaining colony cannot survive on lettuce. It needs energy-dense food: potatoes, sweet potatoes, beans, soy, grains, algae, fungi, possibly insects, and eventually synthetic food systems. Food on a rogue planet would not be romantic. It would be calculated. How many calories per square meter? How much protein per kilowatt hour? How much water is lost? How fast can it grow? How much waste can be recycled? How many people can it feed? A person needs roughly 2,000 to 3,000 calories per day, depending on age, body size, health, and work level. A colony of 100 people may need around 250,000 calories per day or more every day. Without interruption, that means the farm must produce constantly, not once per season, not during harvest time. A rogue planet colony would probably grow crops in rotating cycles, some plants sprouting, some maturing, some ready to harvest, some being replanted. The farm must never stop because there is no outside ecosystem to catch the colony if it fails. And this is why fungi may become one of the most important food sources. Mushrooms and fungi do not need sunlight the way green plants do. They do not photosynthesize. They can grow in darkness, feeding on organic material. That makes them incredibly valuable on a rogue planet. Fungi can convert waste biomass into food. Plant stems, roots, inedible crop remains, and processed organic waste could become substrate for mushroom farms. They can provide nutrients, texture, flavor, and some protein. They can grow in stacked, dark, humid chambers with less lighting demand than crops. In a world without sunlight, mushrooms may become one of humanity's closest allies, not because they are perfect, but because they belong to darkness. A rogue planet diet might include mushrooms every day, mushroom protein, mushroom soups, mushroom flour, fermented fungal foods, engineered fungi grown for specific nutrients. Over time, humans may design fungal strains specifically for closed colonies, fast-growing, nutritious, safe, efficient, and able to process waste streams. Algae would be another essential food system. Algae can grow quickly, produce oxygen, absorb carbon dioxide, and provide proteins, fats, vitamins, and minerals. In underground chambers, algae could grow inside transparent tubes or tanks under artificial light. Unlike mushrooms, algae still need light. But algae are efficient. They can grow in dense systems. They can be harvested repeatedly. They can support both food and life support. Spirulina and other edible algae could become basic survival foods. Not exciting, perhaps, but powerful. Dried algae powders, protein pastes, nutrient drinks, and processed algae-based foods could help keep a colony alive. A rogue planet farm would likely combine plants, fungi, and algae. Each one solves a different problem. Plants provide carbohydrates, vitamins, oxygen, and psychological comfort. Fungi convert waste into food and grow without much light. Algae provide fast nutrition and help manage air chemistry. But for protein, the colony may need something else: insects. For many people, the idea may feel uncomfortable at first. But insect farming is efficient. Insects require less space, less water, and less feed than many traditional animals. They can convert plant waste into protein and fat. They reproduce quickly. They can be processed into flour, protein bars, oils, and animal-like food ingredients. On a rogue planet, cows are almost impossible. Large animals consume too much food, water, space, and energy. Chickens might be possible in a mature colony, but even they add complexity. Fish farms could work if water and feed systems are strong enough, but they require careful management. Insects are simpler. Crickets, mealworms, black soldier fly larvae. These could become part of the closed food chain, not necessarily eaten whole. They could be processed into protein powder, mixed into bread, pasta, sauces, or synthetic meats. The future diet of a rogue planet colony may not look strange on the plate, even if the ingredients are strange behind the scenes. A meal might be a flatbread made from hydroponic wheat and insect protein, a mushroom stew grown in dark chambers, algae-based supplements, potato crops grown under LED lights, fermented foods made by engineered microbes, synthetic fats produced in bioreactors. This brings us to synthetic food. In the long term, a rogue planet colony may not rely only on traditional agriculture. It may use bioreactors to grow food directly. Microbes could produce proteins. Yeasts could create fats. Engineered bacteria could produce vitamins. Cultured cells could grow meat-like tissue. Chemical systems could convert carbon, hydrogen, nitrogen, and minerals into edible compounds. This sounds futuristic, but for a rogue planet, it may become necessary because traditional agriculture is energy hungry. A field of wheat under artificial light is expensive. A bioreactor producing protein from controlled inputs may be more efficient. The colony would eventually choose food systems not based on tradition, but on survival math. How much food per kilowatt? How much nutrition per liter of water? How much labor per meal? How stable is the system? How easy is it to repair? On Earth, food is culture. On a rogue planet, food is culture plus engineering. And the best guide may come from Earth's deep sea. Deep beneath our oceans, sunlight never reaches. Yet life exists around hydrothermal vents. Entire ecosystems survive in darkness, powered not by photosynthesis, but by chemosynthesis. Chemosynthesis is life using chemical energy instead of sunlight. Microbes near vents use chemicals from Earth's interior to create energy. Other organisms depend on them. Tube worms, clams, shrimp, and other deep-sea creatures form communities around these chemical energy sources. This matters because it proves something profound. Life does not always need sunlight. It needs energy. On Earth's surface, that energy usually comes from the sun, but in the deep ocean, it comes from chemistry and heat. A rogue planet colony would follow the same principle. Not biologically at first, technologically. If there is geothermal heat, humans could use it. If there are chemical gradients underground, microbes or engineered systems might exploit them. If the planet has a subsurface ocean, hydrothermal vents could become places of scientific interest and maybe natural ecosystems. A rogue planet may be dark on the surface, but energy could still exist below. And if nature can build food chains from chemistry, humans may one day build artificial food chains from nuclear power, geothermal heat, and controlled biology. The complete food chain would need to be designed. It might begin with energy from reactors or geothermal systems. That energy powers lights, pumps, and bioreactors. Water is mined from ice and recycled. Carbon dioxide from human breathing feeds plants and algae. Plants produce food and oxygen. Plant waste feeds fungi and insects. Human waste is processed into safe nutrients. Microbes recover minerals. Algae and fungi provide additional protein. Insects convert waste into edible biomass. Synthetic systems fill nutritional gaps. Nothing leaves the cycle. Nothing is thrown away. In a place where resupply may be impossible, waste is not garbage. Waste is unfinished food. This closed loop would be the heart of survival. But food is not only about calories. Humans need vitamins, minerals, fats, proteins, fiber, and psychological satisfaction. A technically complete diet that tastes terrible could damage morale over time. Eating the same paste every day for years might keep bodies alive, but it could make life emotionally unbearable. So the colony would need variety, not luxury, stability, different textures, different flavors, fresh greens, warm meals, fermented foods, spices grown in small amounts, comfort foods recreated from limited ingredients. Food would become one of the main defenses against psychological collapse. A meal is not just nutrition. It is routine, community, a reminder that life is more than survival, but permanent darkness creates medical problems too. One of the biggest is vitamin D. On Earth, human skin produces vitamin D when exposed to sunlight. On a rogue planet, there is no sunlight. People living underground would get none naturally. Without supplementation, vitamin D deficiency can affect bones, immunity, mood, and general health. So, every person in the colony would need medical monitoring. Vitamin D supplements would become standard. Artificial UV exposure might be carefully used in medical rooms. Diets would be engineered to prevent deficiencies. But vitamin D is only one example. A light-deprived diet and environment can affect hormones, sleep, mood, metabolism, and immune function. The colony would need nutritionists, doctors, biologists, and automated health systems constantly tracking the population. Blood tests, bone density scans, hormone monitoring, gut microbiome management, mental health support, diet adjustments. Food would become medicine. Light would become medicine. The colony would also need to preserve gut health. On Earth, our microbiome is influenced by diverse foods, environments, and natural contact. In a sealed colony, diets may become narrow and sterile. That can affect digestion, immunity, and even mood. So, fermented foods might become essential. Yogurt-like cultures, fermented vegetables grown indoors, microbial supplements, engineered probiotics. A rogue planet colony would not only feed humans, it would feed the invisible ecosystems inside humans. Now imagine what humans might eat on a rogue planet 100 years after the first colony begins. By then, food would be more advanced. The early ration packs from Earth would be gone. The colony would have mature underground farms, vertical crop towers glowing under artificial suns, mushroom forests growing in dark humidity, algae walls bubbling softly in green tubes, insect protein farms hidden in controlled chambers, bioreactors producing custom proteins, oils, vitamins, and flavor compounds. A kitchen might prepare meals that look familiar but come from completely artificial ecosystems. Bread made from compact grain crops and microbial protein, soups from mushrooms and hydroponic vegetables, algae-enriched noodles, lab-grown meat grown in bioreactors, insect-based flour hidden in baked foods, synthetic dairy from engineered microbes, fresh herbs grown in tiny high-value gardens. To the first generation, this might feel strange. To the children born there, it would feel normal. They might never see an outdoor field. They might learn that food comes from light chambers, growth tanks, fungal rooms, and nutrient loops. Their idea of harvest would not be a farmer under the sun. It would be technicians checking crop towers under LEDs. And yet, if the system works, food could become more than survival. It could become culture, rogue planet cuisine, recipes designed for darkness, celebrations built around harvest cycles, special meals made from rare fresh fruit grown in precious greenhouse space. Maybe one day, a child in that colony tastes a strawberry grown under artificial light and hears stories of Earth where such fruits once grew under an actual sun. That is the emotional weight of food on a rogue planet. It is not just about avoiding hunger. It is about preserving humanity. A colony could have perfect reactors, strong walls, clean water, and safe air. But if it cannot feed people in a way that sustains body and mind, it will fail. Food is memory. Food is biology. Food is continuity. And on a rogue planet, food would be one of the hardest forms of light, because every meal would begin in darkness. A dark world, a buried farm, a reactor humming below, artificial lamps glowing above green leaves, mushrooms growing where sunlight has never existed, algae turning carbon into nutrition, insects converting waste into protein, machines recycling every drop. Outside, the surface remains frozen. No sunrise, no natural seasons. But inside the colony, something impossible happens. Plants grow, meals are cooked, people gather. Children eat food produced on a planet with no star. And in that moment, survival becomes more than a technical achievement. It becomes a quiet act of defiance, a way of saying that even in the deepest darkness between stars, life can still find a way to continue. Finding a habitable rogue planet may be harder than surviving on one, because before humans can cross the darkness, before a ship can leave Earth, before any colony can be built beneath frozen ground, we would first need to find the right world. And that is the problem. Rogue planets do not shine like stars. They do not reflect much light. They do not pass regularly in front of a parent sun. They do not announce themselves with seasons, days, or bright surfaces. Most of them are almost invisible. A habitable rogue planet, if one exists, would not look like Earth from far away. It would not glow blue. It would not show oceans under sunlight. It would not reflect clouds. It would be dark, cold, silent. A hidden planet, moving through the galaxy, without a star to reveal it. So how would we even find one? The main method today is gravitational microlensing. This happens when a dark object passes in front of a distant background star. The rogue planet's gravity bends the star's light for a brief moment, causing the star to brighten in a tiny, temporary way. The planet itself may remain unseen, but its gravity leaves a clue. NASA describes microlensing as a key way to detect planets that are difficult to find by ordinary light, including free-floating worlds. It is like seeing an invisible hand pass across a lamp, not because you see the hand, but because the light changes. That is how we may discover many rogue planets, not by looking at the planets directly, but by watching the stars behind them flicker. Future telescopes will make this search much stronger. NASA's Roman Space Telescope is expected to use microlensing to find many more free-floating planets, including possibly Earth-mass rogue planets, CON. But even then, finding a rogue planet is only the first step. Finding a habitable one would be much harder. We would need to know its mass, its temperature, whether it has an atmosphere, whether it has internal heat, whether it has water ice, whether the surface is stable, whether there is any chance of a subsurface ocean, and most importantly, how far away it is. The James Webb Space Telescope can help in a different way. Webb is especially powerful at studying faint infrared objects, including warm, free-floating planetary mass objects. For example, NASA reported Webb observations of SIMP 0136, a rapidly rotating starless object, roughly 20 light-years away, using infrared light to study its atmosphere and weather-like changes. But a cold, Earth-sized rogue planet would be much harder. It would emit very little heat. It might be almost completely dark. And if it did not pass in front of a background star at the right time, we might never notice it. So the nearest habitable rogue planet could be closer than we think, or impossibly far. We simply do not know. Maybe one exists within a few dozen light years. Maybe the nearest useful one is hundreds of light years away. Maybe there are many wandering worlds near us, but none with the right conditions. And that uncertainty matters because distance decides everything. Even reaching the nearest star system is beyond current human capability. A rogue planet could be closer than many stars, but still far beyond anything we have ever attempted. With today's fastest spacecraft technology, a journey to even a nearby interstellar object would take thousands of years. Not decades, not centuries perhaps. Thousands of years. That means no ordinary mission could reach it. No crew could board a spacecraft, travel there, land, and return within one lifetime. A rogue planet mission would not be like Apollo. It would not be like Mars. It would not even be like a future mission to Titan. or Ganymede. It would be interstellar. And interstellar travel changes the meaning of exploration, because the people who leave Earth would not be the people who arrive. The only realistic transport option, with anything close to current imagination, would be a generation ship, a spacecraft designed not for one crew, but for a civilization in miniature. A ship where humans are born, live, age, and die during the journey. A moving world, a closed society traveling through darkness for centuries. Inside such a ship, life would be completely artificial. Air recycled endlessly. Water purified again and again. Food grown in hydroponic farms. Energy supplied by nuclear reactors or future fusion systems. Artificial gravity created perhaps by rotation. Schools, workshops, living quarters, farms, libraries, governance, culture, everything needed for human life packed inside a machine crossing interstellar space. The first generation would remember Earth. They would know oceans, blue skies, natural sunlight, open air, rain, forests, cities. They would leave with purpose, with fear, with hope. But the second generation would know Earth only through stories. The third might know it through recordings. After many generations, Earth could become almost mythical. The planet of origin, the blue world, the place their ancestors left behind. That is one of the deepest psychological challenges of generation travel. How do you keep a mission alive when the destination is not for you, but for your descendants? How do you teach children to care about a planet they will never see until old age, or never see at all? How do you prevent the ship from becoming a prison in the minds of those born inside it? A generation ship would need more than engineering. It would need culture, meaning, ritual, education, a reason to continue, because the mission cannot depend on excitement forever. Excitement fades. Routine takes over. Centuries pass. Systems age. People argue. Beliefs change. Memories weaken. The ship becomes home. And the rogue planet becomes a promise no living person has touched. Then there are social challenges. A generation ship must remain stable for hundreds or thousands of years. That means its population must be large enough to avoid genetic problems, but small enough for the ship to support. It would need careful medical planning, genetic diversity, family systems, ethical rules, population control, education, conflict resolution, mental health care, a legal structure, a way to handle crime, illness, failure, leadership, and disagreement. Because there is no outside society to help. No emergency evacuation. No second Earth nearby. The ship must carry humanity not only biologically, but socially. If the society fails, the mission fails. And if the mission fails in interstellar space, there is nowhere to go. No rescue is coming. That is the truth of a rogue planet journey. It would be one way in practice, even if the ship was designed to continue, even if it had enough fuel to adjust course. Even if it could send messages back, returning to Earth would be almost impossible. The distance would be too great, the time too long. Communication itself would become strange. If the rogue planet is tens of light years away, a message to Earth would take decades. If it is hundreds of light years away, a message would take centuries. There would be no conversation, no live support, no rescue plan. Earth would become history, a distant origin point, a memory traveling at the speed of light. By the time Earth receives a message saying, "We have arrived," the people who sent it may already be gone. And by the time Earth sends a reply, the colony may have changed completely. This means the crew must become fully independent, not mostly independent. They must repair their own systems, grow their own food, produce their own air, manage their own medicine, make their own decisions, raise their own children, survive their own disasters. And when they arrive at the rogue planet, there is no guarantee it will be exactly as expected. That may be the most terrifying part. Imagine traveling for centuries toward a dark world detected only by distant instruments. The ship has crossed interstellar space. Generations have lived and died. The destination finally grows from a theoretical point into a real object, a black planet, no star beside it, no daylight, no visible surface until the ship shines light upon it. Instruments scan the world. Atmosphere, gravity, ice, heat flow, magnetic field, geology, possible water, possible hazards. And only then does the truth become clear. Was the planet worth the journey? Is there enough heat? Is there water? Is the atmosphere usable? Is the surface stable? Can humans build there? Or did centuries of hope lead to a world too cold, too dead, too dangerous? That is the risk. A rogue planet mission must choose its target with extreme care. Robotic probes would almost certainly go first, but even sending probes would take enormous time. A probe sent ahead might take centuries to arrive. Its data might take decades or centuries to return. Planning would become almost impossible by today's standards. So perhaps the generation ship itself would carry the decision makers. It would arrive, survey the planet, and decide whether to land. The first landing on a world with no sun would be unlike any landing in human history. There would be no glowing star above the horizon, no daylight to reveal mountains, no blue sky, no sunset, only darkness. The landing craft would descend using radar, infrared sensors, LiDAR, and artificial floodlights. The surface would appear only where human technology illuminated it. A circle of light moving across frozen ground. Cracks, ice, rock. Maybe frost, maybe dark plains, maybe geothermal vapor rising from a distant fracture. The lander would touch down on a planet that had never known sunrise, and for the first time, human light would fall on that surface. That moment would be almost impossible to describe. The landing legs settle. Dust or ice particles lift. The engines shut down. Silence returns. Outside the window, the world is black, beyond the reach of the lamps. Above, The stars are sharp and endless. No sun, no parent star, no warm direction in the sky, just the galaxy. A human steps down. The boot touches frozen ground, and the person realizes something no explorer before them has ever felt. They are standing on a planet that belongs to no star, a world completely outside the architecture of ordinary life. But landing would not mean success. It would only begin the next test. The colony would need to build quickly. Power first, then heat, then shelters, then drilling, then water extraction, then food systems, then permanent habitats. If the planet has geothermal energy, the colony must find it. If water is buried, they must reach it. If the atmosphere is dangerous, they must seal themselves from it. If the surface is unstable, they must move. And if something goes wrong, there is no rescue, no backup ship arriving next month, no emergency return to Earth, no mission control solving the problem in real time. Only the people there, only the systems they brought, only the planet beneath them. That is why the journey to a rogue planet is not just travel, it is separation, a complete break from Earth. The crew would not be explorers in the old sense. They would be founders, the first humans to attempt survival on a world with no star. And if they succeed, their descendants may one day look back at the landing as the beginning of a new branch of humanity, a people of artificial dawns, a people of underground cities, a people who learned to live by geothermal heat and nuclear light, a people born under stars but never under a sun. But if they fail, the rogue planet remains dark. The ship becomes silent, and Earth may never know the full story. That is the cost of such a mission. It is not simply expensive. It is irreversible. A journey to a rogue planet would require a level of commitment humanity has never made before. Not a mission measured in years, a mission measured in generations. Not a crew going to plant a flag, a society going to become something else. And that may be the most honest answer. Could humans travel to a rogue planet? One day, maybe, but it would not be a trip. It would be an exile chosen with hope. A one-way crossing into the dark toward a world that may offer no sunrise, but perhaps beneath its frozen surface, a chance to survive. At first, the idea feels almost absurd. Why would anyone choose a rogue planet? Why would any civilization leave a star system with sunlight, warmth, planets, moons, and familiar rhythms for a frozen world drifting alone in the dark? Why choose a place with no sunrise, no seasons, no daylight, no natural sky? Why build a future on a world that the universe itself seems to have abandoned? The answer is not comfort, it is survival. Because a rogue planet may be one of the most hostile homes imaginable, but it may also be one of the safest. That sounds strange at first. A planet without a star feels unsafe by definition. No energy from above, no natural warmth, no photosynthesis, no day, no easy surface life. But stars are not only sources of life, they are also sources of danger. A star can flare. A star can bathe planets in radiation. A star can swell into a red giant. A star can die. A star can explode, depending on its mass. A star can transform everything orbiting it. Earth is safe now because our sun is stable. But even the sun is not eternal. Billions of years from now, it will change. It will grow brighter. It will make Earth harder to live on long before it becomes a red giant. Eventually, the inner solar system will no longer be the gentle home we know today. And when that future comes, humanity, if it still exists, will need choices. Move outward, move underground, move to other stars, or perhaps find worlds that do not depend on stars at all. That is the strange safety argument for rogue planets. They are dark, yes. Cold, yes. Difficult, yes. But they are not tied to the life cycle of a nearby star. No stellar flares ripping through the sky. No sudden increase in solar brightness. No parent star aging toward destruction. No habitable zone shifting away. A rogue planet is not safe because it is gentle. It is safe because it is stable in its darkness. A world drifting between stars may remain almost unchanged for billions of years. If it has internal heat, water, a thick atmosphere, and usable resources, it could become a kind of cosmic bunker, not a paradise, a refuge, a hidden world where a civilization could survive away from the violence of stars. This idea is unsettling because it changes how we think about home. We usually imagine the future of humanity among bright worlds, Mars under a pale sun, Europa under Jupiter, Titan beneath orange haze, exoplanets orbiting red dwarfs, Earth-like planets around distant suns. But a rogue planet asks a darker question. What if the best shelter is not near a star at all? What if the safest place for a civilization in the very long term is underground on a world that no sun can destroy? Imagine a future where humanity has spread beyond Earth. We understand fusion power. We can build closed ecosystems. We can recycle water, air, and nutrients almost perfectly. We can live underground for generations. We can travel between stars slowly but deliberately. In that future, a rogue planet would not look only like a dead world. It would look like storage, protection, raw material, a planetary fortress in the dark. Its surface may be frozen, but that frozen shell could protect what lies beneath. Its lack of sunlight may be terrifying, but it also means there is no stellar weather. Its isolation may feel lonely, but it also makes it quiet. A civilization living inside such a planet would be hard to threaten from outside. The world would not glow brightly. It would not advertise itself. It would drift silently through the galaxy, carrying cities beneath its crust. The ultimate bunker, a place where life hides from the universe. And if our sun were dying, or if Earth became uninhabitable, a rogue planet could become one of many backup possibilities. Not the first choice, probably not the easiest, but one of the most enduring. Because in the far future, survival may not be about finding a perfect world. It may be about building one. A rogue planet would force humanity to stop depending on nature's generosity. No free light, no free warmth, no open atmosphere we can trust, no crops beneath a sky. Everything must be designed. Energy, food, water, air, medicine, culture, psychology, time itself. And that brings us to the philosophical question: why do humans try to survive at all? Why do we keep imagining futures beyond the places that made us? Why not remain where we are, under the sun that created us, on the world that shaped us? The answer may be that survival is one of the deepest instincts life possesses. Every living thing continues, if it can. Roots search for water. Cells repair themselves. Animals migrate. Humans build shelters, tools, stories, cities, ships, telescopes, rockets. We are not the strongest species, not the fastest, not the most durable, but we are adaptable. We survive by imagining conditions before they arrive. We build futures in our minds before we build them in reality. That is what makes the rogue planet idea conceivable. Not because it is easy, but because humans have always learned to live where we were not expected to. We learned to live in deserts, in ice, on islands, in mountains, under oceans for months at a time, inside submarines, in orbit, above Earth, inside metal stations. Each step taught us that home is not only a place, home is also a system, a structure, a community, a way of carrying what we need into places that do not naturally provide it. A rogue planet would be the most extreme version of that truth. Choosing permanent darkness for survival would be one of the most profound decisions a civilization could make, because it would mean accepting that comfort is not always the same as safety. It would mean giving up the oldest symbol of hope humans have ever known: sunrise. For all of history, dawn has meant continuation. The night ends. The world returns. Light comes back. But on a rogue planet, dawn never comes. If humans lived there, they would have to create their own dawn underground. Every morning would be artificial. Lights rising slowly in habitat ceilings, warm colors changing by design, children waking beneath simulated skies, plants opening under LED suns, music playing to mark the beginning of a day that the planet itself does not recognize. Time would no longer come from the sky. It would come from culture, from clocks, from rituals, from shared agreement. And after generations, the people born there might not miss sunlight the way Earth-born humans would. They might know it as history, as myth, as something seen in recordings. They might grow up under artificial blue ceilings, inside caverns, warmed by reactors and geothermal heat, learning that outside the walls lies the endless dark. Their idea of beauty would be different. They might find comfort in the stars, in the silence of the surface, in the glow of their cities beneath ice. They might celebrate reactor renewals the way we celebrate harvests. They might write poems about artificial morning. They might paint with colors inspired by bioluminescent gardens, greenhouses, auroras from distant interstellar particles, and the glow of human-made light against black stone. Their music might sound different too, less shaped by birds, oceans, and wind, more shaped by machines, echoes, tunnels, heartbeats, and the soft hum of life support systems. A lightless civilization would not be without art. It might create art more intensely, because when nature gives no color, culture must create it. When the sky gives no sunrise, music must become sunrise. When the surface gives no warmth, architecture must become warmth. Their philosophy would also change. People on Earth often think of the universe as something above us, a sky, a vastness overhead. But humans on a rogue planet might think of the universe as something outside the walls, cold, beautiful, unreachable without protection. They might see life as something fragile that must be protected deliberately, not assumed, not taken for granted. Every breath would remind them that life is engineered. Every meal would remind them that survival is cooperation. Every child born there would be proof that humans can carry continuity into places nature never prepared for us. But would they still consider themselves human? At first, yes. They would speak human languages, carry human history, tell stories of Earth, remember oceans, forests, sunlight, and the first home. But after centuries, after thousands of years, things might change. Their bodies might adapt to underground life. Their culture would be shaped by darkness. Their sense of time would be artificial. Their relationship with Earth might become distant, almost religious. They might no longer think of themselves as exiles from the light. They might think of themselves as the people who learned to live without needing it. Still human, but changed. A branch of humanity shaped by a world with no sun. And maybe that is not a loss. Maybe that is what survival always does. It transforms. The first humans who crossed oceans became different from those who stayed behind. The first humans who settled frozen lands changed their tools, clothing, myths, and ways of life. The first humans born beyond Earth will also change. A rogue planet civilization would simply be the most dramatic version of that ancient pattern. Life entering a new environment and becoming something that environment can hold. So should we consider it? Not now, not soon, not before easier worlds, not before Mars, the Moon, Titan, Europa, or the stars nearest to us. A rogue planet is not a practical destination for our current civilization. It is too far, too dark, too difficult, too final. But as an idea, as a distant possibility, yes, we should consider it, because considering it forces us to ask what survival really means. Is humanity only a species of daylight? Only a species of one star? Or could we become something wider? A civilization that does not simply search for perfect homes, but learns to build them in impossible places. The answer may take thousands of years, maybe longer. But the question matters now, because every future begins as something that once sounded impossible. A city beneath ice on a rogue planet. Artificial forests under nuclear light. Children born on a world with no sunrise. Music echoing through underground halls, while above them, the galaxy turns silently. A civilization hidden in darkness, not dying there, but living. There is something hauntingly beautiful about that, because a rogue planet is the opposite of everything we associate with life. No sun, no day, no warmth from the sky, no natural garden. And yet, if humans ever survived there, it would prove something extraordinary. That life is not only where the universe is kind, life can also be where intelligence becomes patient enough, careful enough, and brave enough to protect it. Tonight, as you drift to sleep, somewhere in the darkness between the stars, a world is wandering. Alone, cold, silent. No sun has ever risen on its horizon. No star has ever lit its sky. And yet, it may carry within it everything needed for life to continue. Water beneath ice, heat beneath stone, energy waiting in the dark, a future hidden below a frozen surface. It just needs someone brave enough to find it and call it home.